Okay, thank you very much. Thank you, Tanya. First, I would like to acknowledge the Trump Foundation Award to make it possible for me to travel to Barcelona to share my knowledge with everyone. And I'm Peng ZHIKAI from China, but I now work in the Netherlands with my colleagues. I'm also representing Daniela Majolari, and we are two assistant professors in Delft University of Technology. I'm from architecture department, and she's from urbanism. And our scale match each other at the street scale, which I present this topic, cooling effect and skin temperature recovery in urban environments. So we talked a lot of things about extremes, about mortality, about morbidity. And I want to bring you another angle at non-extreme conditions, which means we always experience rise and falls of temperature of our human body. Not just the extreme moment, also non-extreme moment. We cannot escape our thermal experience. So let's talk about those non-extreme everyday thermal experience. That's also part of the citizen science I'm dedicated for. So this presentation will be divided into two parts. And the first part, I will discuss these questions. How does human skin temperature respond to sun and shade? Here I rephrase it, urban heat and tree shade for the first project. So we always experience tree shade. So this is a very intuitive experience for you to imagine. If you barefoot, you step in the sun, step in the shade, you can feel the differences. And sometimes you feel pleasure. That's how your skin responds to take the information from the environment and respond to the environment. But we don't always walk barefoot. We walk from head to toe. We experience, we absorb the air. So it is very important to collect our information physiologically, every part of our body. So first we consider what kind of data we can gather from the environment, also from our body. So this project, we have engaged 8 Dutch municipalities, and here today I'm just going to present one municipality from the city of The Hague, and we work with 3 species, the most common tree species in the Netherlands, and they thrive, defoliate in the winter and thrive in the summer. Here we use the Tilia. It's also called Pollense linger. We are going to select what kind of urban environment we are going to do our physiological test. There are 2 kinds, urban green spaces, and here we present the street. Why we only choose the east or west street, but not the north or west? Because there were more overlapping between the building shade and tree shade. So we're only presenting the east or west streets for understanding tree shade and skin temperature recoveries. And the experiment has been divided into 6 groups. Then deployment of the sensors, we have 2 levels, one at ground levels. We measure air temperature, relative humidity, globe temperature, and wind speed. And also we have ground level sensors, that's the more longitudinal year-round sensors. Here we are not going to present data because we are not able to fly to the ground level. So only we are going to see the ground level sensors. And here comes the most interesting part. We task participants to swap between the sun and the shade to see their skin temperature resistance and recovering the time series. And we are going to measure 2 variables, skin response and a metabolic rate. So before the real-world measurement campaign, it is very important to understand, to do some preparations to understand if our tree has overlap with the building shade, and where can we put our sensors without those confounding effects. And we also do a controlled experiment within a container portiere to understand the diurnal surface of the tree shade and also the surface temperatures. So here, that's the result. We decided to put 1 Kestrel sensors in the sun in the yellow point, and for the kestrels in the shade, it's a bit tricky because tree shade move every 10 minutes almost.
Sorry for the interruption. Yeah, this is the result, and we have to move the shade, the sensors in the shade every 10 minutes to align with the center of the tree shade. That's for the environment measurement. And for the human measurements, the two participants will be moving between sun and shade, also align with moving the sensors in the tree shade every 10 minutes. So we are very interested to see their skin temperature recoveries, the intermittent warming and the intermittent cooling. Here are some matrix we use. The first, there are two variables for environmental heat stress. One is UTCI, the other is PET. And for the human matrix, we use 8-point mean skin temperatures. We tape eye button thermochromes on 8 different body locations according to the international standards. And we also compare the difference between two thermal indices, UTCI and PET. And I think we have a very good discussion on Monday about the occasion when to use these indices. And I think I know from you that UTCI is more designed for the cold climates, and PET, you have more subjective personal parameters. But here, these two indices doesn't consider any personal parameters. We use it to define the thermal contrast between sun and shade. And we overlapped our skin temperature time series on top of them. And here are the results. We see in the context of the Hague, that's the temperature difference between sun and shade are not too much, only 1.2 degrees of difference. But we see the perceived temperature contrast are very big. For UTCI, it can be more than 10, and PET more than 15. So that means the radiation and also wind can collectively shape our overall thermal experience other than the air temperatures. We also checked other literatures to find if the spectrums of the PET and UTCI align with our results. And although the explanations are from different perspectives, but the results are aligned. We also lay our physiological data on top of the environmental measurement. We have 2 participants, although this is a very exploratory studies that we only have 2 sample size. We still can find some very interesting findings from these 2 time series curves. We see that 2 participants, generally, their physiological response to the heat stress rise slowly from the morning 11 o'clock to the afternoon 4 o'clock. However, the range of their skin temperature fluctuations and the slopes are very different. And we try to relate indoor or controlled semi-outdoor experiments to our findings. Why those 2 participants behave so differently? Because our experiments are not strictly restricting their freedom to go to toilet or have a break. So we find that those confounding variables are very, very valuable to carry out our citizen science project in the future. For example, we see after the lunch break that 2 out of their physiological response are diverged. One participant had much higher skin temperature at the end of the day, but the other still remained the same. And that's possibly because of the sweating ratio. We know if we sweat, the skin temperature will go down. So that's something, also a knowledge we want to disseminate at citizen level. So, second project, something new. I haven't presented this project on Monday, but I want to share with you because previous experiments we only contain 2 sample size. That's not enough to conclude anything. But here we have 40 participants. That's an experiment I've done in Rome 2 years ago, 3 years ago during COVID. And I try to replicate the same approach while people walking in the city. So I'm trying to understand not only tree shade, but also building shade. So urban climate walk project in the city center of Rome. First, it's really important to understand why our tourists, our visitors, or if you go to a historical town, you always feel kind of sense of pleasure, positive feeling, walking to the church, walking down the tree shade, or go to a street market, although there are some. Why is that? I try to relate the theory of thermal anesthesia. Anesthesia means change of sensation. That's a Greek word. If your temperature goes a little bit up and go a little bit down, those keep moving. That's good for you. And if you stay in an air-conditioned room all day long without changing air temperature, you feel bored. So that's the motivation for me to do this project, to see which urban spaces are perceived as pleasurable, which perceived as boring. And of course, this is just one illustration. The real context, here is the methodologies. So I task participants to walk and stop at different anchor points along designated routes. Could be tunnel, bridge, urban green spaces, waterfront, of different microclimatic conditions. And they have to do two things. First, they take with sensors. I log their skin temperature. And the second, they have to fill the surveys, right here, right now surveys. How hot you feel, how happy you feel, how boring you feel. And environmental measurement, how we gather those data, we tasked participants to relay two sensors, because this experiment is solely conducted by me and without any assistance. So I coined these protocols. They relay the two Kestrel sensors from point to point. First, we can have the acclimatization time. While their body is acclimatizing, the other Kestrel sensors are waiting in the next point for them. So that's one strength of this method. The other is COVID rules. I can keep distance with them at the next point without social. That's a specific time, specific rules. So there are two designated routes. One in the left side is in the density center, and the other is in around 7 kilometers away in the suburban. So due to the urban heat island effect, the temperature on the left district is 3 degrees warmer than on the right side. But we see the fluctuations of UTCIs are totally different. We see more fluctuations and more intermittent cooling and warming in the dense district, but much less very big rise, big fall, slow rise, slow falls UTCI in the suburban district. So that's define the baseline for us to understand physics, just the physics. And next step is to see the physiological response to the rise or falls of environmental physics. And we see that on the left you see that although they have very different urban heat island effect, that the speed, the variability of the skin temperatures, the recovery of skin temperatures for two groups are same. If you look at the slope, look at the slope of those two curves are the same. However, if you look at walking conditions, that they lead from one point to another, that two districts have shown very different physiological slopeness. That dense cities would have much higher, so I would say the roller coaster effect than the suburban district. So that's the physiology. And the last evidence is psychology. It's from their mobile surveys. How boring, how interesting you feel, that's one question. And also the TSV, the most classic indices psychometrics we use, thermal sensation volts. So first, it's very interesting to find that although the urban heat island effect indicates dense cities are 3 degrees warmer than suburban, the TSV show different results. People feel cooler in the density. I guess because I don't have an interview session to validate why because they vote like that, but that's part of my speculation. It's because of the intermittent cooling and warming give them more opportunity. Shading, of course, sun and shade, the opportunity to swap your thermal conditions that give this results. And also you see on the right side is the how long do you wish to go stay here? Of course, we see also similar findings, but this psychometric is a bit problematic because we are here only examining thermal conditions. In real life, real world, you taught citizens to answer those questions. They've probably been confounded by non-thermal factors. So that's part of the scientific challenge for us to conduct in situ thermal studies. So to conclude, first I present quite controlled tree shade experiment on the left side. We see that PT is a quite intuitive indices in citizen science to illustrate that the difference between sun and shade can be 15 degrees difference. And second, their citizens' skin temperature can be as wide as 3 degrees difference between sun and shade. And sweating can significantly confound and disturb the skin temperatures. That's quite controlled findings. And on the right side is my experiment in Rome. So first, dense urban areas, building densities are not necessarily bad things because they provide additional intermittent cooling and warming opportunities. And second finding is those intermittent cooling are very important for both physiological and psychological adaptation, warp and stop. And finally, visual confounders are something we really annoyed scientists. But architects, we feel excited about visual confounders. So if you heard about placebo, nocebo effect, that's something we architects are very happy to utilize. But we also find good confounders and bad confounders. For example, small water bodies, that's actually doing bad things. People think that make them more hot because the body is there, you cannot use it. However, there are also good confounders like greeneries. If you see a part of greens, they really improve the visual and thermal, part of future research questions to understand visual and thermal interactions. So I would like to acknowledge those 40 participants. I recruit them from 5 Facebook group, or hiking and walking. I just Google Facebook groups. They are open access, and I posted my participant there. They are very happy, voluntarily engaged in this experiment in Rome. And I met some of them yesterday in the fiesta. And we are planning on another rounds of citizen science planner walk. So that's my presentation. Thank you very much.